Morning, everyone. So today we're going to finish off section C2. Yesterday we started looking at fossil fuels in general, how when we dig it deep out of the ocean or out of the ground, basically the crude oil comes to us as a huge mixture. We run it through a fractional distillation column. Basically what happens is we end up vaporizing all of them just with heat, and as that mixture of gases here ends up rising through the column, depending on the size of the molar mass, the heavier molar masses have higher dispersion forces. With higher dispersion forces, they have a higher boiling point. So as the gases then start rising through the column and getting farther and farther away from the heat source, they end up actually condensing at a much lower layer. The things that are tinier, usually the C5s and C10s that we want, because they're a smaller molecule, they have small London forces, and therefore they make it higher up the column before they condense, if they condense at all. Remember, just to keep in mind here, from ethane to butane, C1 to C4, those ones here remain gases even at room temperature. Those ones are used for very common, like barbecue stoves, things like that. So we do manage to make use of all of them, but specifically when we're looking at sort of car engines and fuels, we specifically desire the C5 and C10. Out of the fractionating column here, unfortunately, we don't get a huge quantity of the sizes that we want. So what we're going to do in this lesson here is we're going to learn of a few different chemical techniques. Again, this is just a broad stroke. There's going to be a lot of details in it. But basically, it's going to take things that are much larger. We're going to do a process called cracking. So therefore, I'm going to take a bigger compound and crack them into smaller ones. Or if I have smaller ones, let's say it's a straight chain and it doesn't burn really well, it has that knocking problem we mentioned yesterday. Maybe I want to reform them, isomerize them, make rings of them to try to improve their octane number. Remember, octane number was a scale that I used. I put 0 for burning heptane. I put 100 for burning isooctane, which is 2,2,4 trimethylpentane. And basically, the grade of the fuel here represents burning a fuel that's sort of part isooctane and part hexane. So let's just have a look here at cracking and reforming. In this case here, cracking and reforming are two different methods of improving the quality. We're going to change the molecular structure. For cracking here, it can be done via different ways. We're going to start off with just thermal cracking. So this is, again, not the heat for vaporizing and separating compounds. We've already isolated a certain size of compound, and now we apply high temperatures yet again. And in this case here, this thermal degradation or thermal cracking ends up breaking a long hydrocarbon into two or more shorter ones. So here's some examples here. They take octane here, which is C8, forms a butane and an ethene. This octadecane, so C18, actually breaks them into a couple other ones here. What we're going to start seeing is in these formulas, you'll notice that when you do this cracking, when you break up a single bonded alkane, you're going to find that only one possible alkane is possible as a product. All the remainder are alkenes. We're going to do a proof later on when we switch over to our notes why that's the case, but especially when you're dealing with cracking reactions, yes, cracking means big thing is broken up into small things. Make sure you note that it's only and always one alkane. The rest of them have to be alkenes. The types of cracking, so how do you manage doing this breaking of bigger molecules into tinier ones? We talked about thermal cracking, so applying heat to it here. It usually does involve higher pressures as well. Usually we're under 1 atmosphere pressure, so we need a little bit of a pressure treatment as well. Steam cracking here, steam is the presence of water vapor as well, so actually using water to actually almost like adding to alkenes, but in this case here we're just breaking alkanes into smaller parts. Or like I mentioned, a lot of these processes here are catalyzed by many different chemicals. In this case here we're going to call a generic type of catalyst here called zeolites. Zeolites are naturally occurring minerals of aluminum and silica. Make sure you note these ones here, aluminum oxide and silicon oxide as well. That's the types of cracking here. We're going to see in a little more detail. Big things end up forming small things. What about the reforming case here? For reforming, what we want to do is we want to do a form of isomerization. Basically, we had said the straight chain alkanes here, these ones here don't tend to burn very well. What we're going to do is we're going to run it through some reactions to try to make structural isomers, break some bonds, reform them in such a way that a straight chain, again over a catalyst here, in this case here of aluminum chloride, it's going to separate them and it's going to reattach, it's going to form more branching. Where you're going to find that is over the course of the isomerization case here, not all of them would necessarily be isomerized right away. I might still have a mixture. I would need to separate these guys here. These guys here, because they're isomers to each other, they're going to be very similar. They're going to be nonpolar. They're going to have relatively low boiling points as well. But given the sort of, as I get more branching, it tends to sort of compact on itself here. The London forces get ever so slightly weaker. We can even utilize that to separate off the branched isomers, and then I cycle this mixture here back in, run it through isomerization again, and so therefore reform these products here. Some more specific types of reforming here, that was forming structural isomers. I can do a type of reforming, in this case here, called cyclization, which is basically taking something that's straight and then forming cyclic molecules. Remember, when I form a ring, I end up having to ditch 2 hydrogens so I can connect the ends. So they're no longer structural isomers, but I do end up forming a ring. This one here is also catalyzed by our zeolite, our aluminum oxide, in this case here with platinum as well, under high temperatures, higher pressures. Cyclization just involves forming a ring. And then if I further go to aromatization, basically forming an aromatic compound, meaning basing off of benzene. So these are ways I can convert just straight chain things that don't burn really well into branched things, into rings, these arene rings here, to end up burning better and increasing the octane rating. A couple other big ideas that we're going to see in this section. Coal has a major disadvantage that even though it is a high energy source, it stores a lot of energy inside. Usually when I try to extract the energy, usually I need something big scale, like a big power plant. It can't be just put directly into your car engines. It doesn't release the energy quick enough or safe enough for us to use. So what we're going to do is we're going to take coal, which is primarily carbon. The percentage carbon has been increasing every time I've been processing it. There's going to be 2 things what I can do here is I can take that solid coal. What I can do is I can either gasify or I can liquefy them. As the name suggests, I'm going to form sort of a gas product with carbon in it, a liquid product with carbon, and those ones are going to be more so, for example, liquids are going to be like liquid fuels, a lot easier to store, a lot easier to transport. I'm going to liquefy what would have been really hard to work with, that you mentioned the term here, in situ. In this case here, we're going to chemically convert them, still going to be a carbon source, and we're going to burn those carbon sources. So let's first look at coal gasification here. So coal gasification involves just reacting carbon with water. We're going to get a mixture here of hydrogen and CO. This mixture here is called synthesis gas. So make sure you know that name there. It's a combination of carbon monoxide and hydrogen. This coal gas is a gas that's formed from a carbon preliminary ingredient here. This one here, the synthesis gas here, is a combustible fuel source. So I can burn these much easier because they're already gasified. They become gases. Or in contrast here, we can do a liquefaction here. I can take the synthesis gas from earlier. Right? I had reacted carbon with water to form the synthesis gas. And basically these guys here, not only can I use these ones here directly, I can run them through another reaction. This can be any number of however long chains, like however many carbon monoxides, however many hydrogens. It does a balancing for you, and eventually we're going to end up with alkanes. You see our general formula for alkane with a 2n plus 2, and therefore we've taken what would otherwise be just carbon, which is really hard to access by itself. We've gasified that, and now we've liquefied it. Keep in the back of your mind here, if the N here is C1 to 4, the alkane here has relatively low boiling point, so those ones will remain gases. That would still be coal gasification. If I really wanted to get a liquid feel that you can pump into your gas tank, you definitely want somewhere between C5 to C10. That's usually our ideal hydrocarbon length. So these guys here, so we're using the synthesis gas. Another way I can do liquefaction here is I can take just a plain old carbon, also react it this time just directly with hydrogen, so no carbon monoxide around. Again, the N and the N plus 1 give us the ratio to. These ones here are catalyzed by iron as a catalyst, and then we also form an alkane. So basically the idea here is we want to increase the supply of our C5 to C10, which we really want to utilize for our fuels. I know over time it's going to be used up, right? It's a non-renewable source, but for the time being it is generating a lot of good energy. Lastly here, as we do talk about carbon sources, especially after burning, we end up releasing a lot of carbon monoxides, carbon dioxides into the air. We want to talk about something called the carbon footprint. Our carbon footprint is essentially the impact that we are for the whole year, so it's annual, from our human activities, from our cooking, from our travel, from our industry, things like that. What is the total amount equivalent of carbon dioxide that we are putting into the atmosphere per year? And that is typically seen as some measure of, it's increasing our greenhouse gases. It may be one of the factors that cause global warming, so it's the one thing that you need to watch out for. Again, some key features here we were talking about here. There's an equivalent ton of carbon dioxide. We may not actually be producing it exactly as CO2. Maybe it's released as water, maybe it's released as N2O, things like that. But we're going to see on the next slide here the reason why we can do equivalent tons of carbon dioxide. Every molecule that we have in the atmosphere, a lot of them are naturally produced, some of them are anthropomorphic and from industry, whatnot. Every one of these here has a global warming potential. We're going to also call this a greenhouse factor on our notes later on. And basically, we're going to set CO2 as our standard. CO2 has a global warming potential of a 1, or a greenhouse factor of 1. Water, even though it is our most common greenhouse gas, it's the most abundant gas inside our atmosphere. We naturally get it from evaporation from oceans. It only has a global warming potential of 0.1. So I need 10 water molecules to be equivalent to 1 CO2. While I may have other molecules like methane, the methane molecule itself, while I may not have, in terms of abundance, very high, it's not as high concentration as CO2. If I have one CH4, that has the impact, it has the effect, a greenhouse factor of 30, it's like having the equivalent of 30 carbon dioxides. So you're going to see when we calculate carbon footprint, we actually want to do equivalent tons of carbon dioxide. And as you go down from there, you see some sources. From fertilizers, we get N2Os, CFCs I mentioned from old refrigerations. That was the thing that caused a lot of chloride radicals. Those chlorine radicals here would actually run through a chain mechanism and destroy ozone. That's what we saw back in chapter 4. In this case here, we're seeing those CFCs also have in itself a huge 20,000 global warming potential. So the textbook that he took a snapshot out of here, he says sort of, although this global warming here is as the name suggests, a universal, it's a global problem. Places, first world countries, third world countries and whatnot, their carbon footprint may be different. Just because we're producing a lot of carbon dioxides in first world countries doesn't mean necessarily only we suffer the effects. The atmosphere will blow these carbon dioxide gases around, and basically it becomes more of a global issue and something that we need to collaborate on together. So in the States here, we have a carbon footprint of about 20 equivalent tons per year. Again, it's quoted per annum. India here is 1. Google, I don't know what's included in all these activities, but they say some 1,500,000. The iPhone and that product there, we get just a relative comparison of this carbon footprint. So we're going to have a look at our notes again, mainly looking at these, the cracking and the reforming, and as well ending off with this carbon footprint. Okay, so let's have a look at what your textbook describes and goes into a little more detail for this cracking section. So we did some of this fractional distillation stuff in an earlier lesson. We're about partway down here. We're going to start here. In fact, we had the most demand in terms of our fuels for, I would say, C5 to C10, but they're just saying relatively some of those lighter ones, C1 to C12, because these ones here typically make the best fuels. Again, make a note to yourself, we wrote this down yesterday, C1 to C4, those are still gases in regular exposure to them. The reason why C5 and C10 are good is because they are liquids, really good to store, really safe to work with, really convenient to transport around. So they also have high combustion enthalpies, really easy to vaporize. Remember we said out of the fractionating column here, unfortunately we don't tend to get a lot. That's really the C5 and C10 that I need for my fuels. So what we're going to do here, like I said, is in chemistry, we're going to take bigger compounds. Cracking always takes something that's bigger and then cracks them into smaller hydrocarbons. So in this case here, we mentioned just in passing yesterday, we can increase the supply. We can get more of the C1 and C12 by taking larger compounds and doing this cracking. They mention on the slides here many different types of cracking. Let's say this is the first method. We can just do thermal cracking, meaning using heat. We knew the term here cracking just meant you're taking a breakdown of larger molecule. And again, they give you some samples here. These are not the only possible products. You don't always need to break up necessarily into two, but they give you some examples. For example, this middle one here, this is a really heavy hydrocarbon here, which would have been condensed on a much lower layer. By doing this cracking, I notice I get C8H18. What's so special about this guy here? This guy is octane. Maybe it might be a straight chain right now. Maybe it's not so good to burn. But if I can isomerize it, if I can form a structured isomer, I might be able to get the isooctane, that 2,2,4-trimethylpentane, which we set as octane number 100. So just giving you some examples of cracking. Other ways that can happen here is they can do hydrocracking. So hydro means you're actually reacting it with water. Actually, in this case here, not specifically the water just yet, but this one here is with hydrogen, but definitely a lot of these require high pressures. In this case here, we talked about doing catalytic cracking. I don't know if I introduced that term for you here, but for catalytic cracking, maybe I can put it down here. For a third one, if you end up using catalytic cracking, it does mention a little bit earlier as well, but basically you're going to use catalysts. Make sure you know this word here, zeolites. They're naturally occurring minerals, aluminum, silicon, and oxygen. They have a really extensive crystal network. They generally have that big covalent lattice structure. For example, for SiO2, it's very similar to our diamond example. SiO2 actually has silicon bonded to 4 other oxygens. Why isn't it SiO4? It's because this one here, as that metalloid, it actually, yes, on average, is bonded to 4 other oxygens, but by ratio in the compound, it's like every Si only has 2 oxygen neighbors. So we still say SiO2. Other common words for SiO2 are silica, or even I might call it quartz. And that is used as a catalyst. Really extensive network. It's like a lattice, but has the advantage of being covalently bonded. And basically what ends up happening is using these zeolites as surfaces, we can crack our alkanes on top of the surface. Again, by cracking, we can form smaller carbon chain lengths that we want. Sometimes when you're trying to crack it, however, some of the sort of offshoots and you're getting like carbon as byproducts, sometimes unfortunately it ends up coating the surface of the zeolite. We needed the surface to actually do the catalysis for us, so therefore that carbon might actually interfere with catalytic action. That's why sometimes we do a mixture of catalysts. Sometimes we do them at high pressures to try to improve the reacting conditions so that the catalyst is sort of maximally suited to it. There was one slide here on the slides that said, when you do cracking, we always generally only form one alkane. The rest of them have to be alkenes. I don't know if you had a chance to actually think about why that's the case. Let's just do one sample alkane here. Let's take butane. Now, butane itself by itself is a gas. I know it's not that long. I can probably use this directly as a fuel. We do it all the time in barbecues and whatnot. Butane so far has a formula C4. We do the 2n+2, so C4H10. Let's imagine I do a cracking process. Let's imagine I have a zeolite surface, some sort of porous material that can accomplish this cracking for us. It can end up breaking bonds for us. So let's start off with the analysis here. Let's say the butane comes close enough to the zeolite and it ends up breaking this middle bond here. Let's pretend that's homolytic fission for now. You'll notice, great, we've done cracking. I've done C4H10. I end up producing 2 things. We end up one guy that's C2H5. The other guy is also C2H5. However, we actually have a radical on both sides. If I were to end up forming 2 alkanes, what I would actually need is I would actually need extra hydrogens. I need hydrogens to add on there, hydrogens add on here. In this case here, cracking, with the exception of sort of hydrocracking, which actually involves hydrogen here. No, cracking actually doesn't involve an extra source of hydrogen. So in this case here, if I do a homolytic fission here, I end up with radicals. These would be super unstable. That would sort of help it do the branching later on. You could think about this fission as happening sort of like a heterofission. So basically both electrons go to one neighbor. So basically what can happen here is maybe this carbon on the right hand side here ditches the hydrogen. Maybe this lone pair grabs the hydrogen and this electron ends up becoming double bond. Sure, we can understand how we might be able to form one alkane. I would then have C2H6 on the left side, and on the right side I end up forming C with the double bond. So what, I have sort of not enough hydrogens, but I can form, again, maximum, I can only form one alkane. And the remainder, I can break up into many different things here. We might end up forming many alkenes. There's actually a mathematical way you can derive this as well. You can start off with our general formula. Our alkane, I would expect, is fairly long. Let's say our alkane has a general formula, CN2n+2. Let's imagine this alkane breaks off into 2 parts. And let's call one of the chain lengths here X. So in this case here, hypothetically, let's say this is an alkane. If this chain length here were X, then I would have H, 2x+2. The remainder of the chain here would be C, n minus x. H, I can double the n minus x. Again, you don't need to repeat this math, but this is just a nice little derivation here. And therefore, if, hypothetically, one alkane can be broken up into more than one alkane, I should be able to add up these guys here, and I should be able to just look at the hydrogen numbers. Well, how many I would need is 2x+2 from the first alkane. I would need a 2 times n minus x plus 2 for the second alkane. We'll see what the general formula is after we do this. So I'm going to get a 2x plus 2, and I'm going to add 2n minus 2x plus 2. Notice in this case here, I don't necessarily know what the x is. I don't even know how big this alkane was initially, but the 2x cancels the 2x, and then my general form would need to be 2n plus 4. This is the number of hydrogens, and we see that, well, wait, alkanes don't have 2n plus 4. I don't have enough hydrogens. So just to prove to you here, don't have enough hydrogens for more than one alkane. So generally when you do this cracking, generally when you separate this compound, we do tend to get one alkane. One thing takes the hydrogen like I just showed you, and the others are sort of revert to doing double bonding and forming alkenes to sort of make sure they fill the octet. So with that in mind here, that explains our cracking. We have the 3 different types here. The cracking rearranges atoms. We talked about nice thing is doing the branching. Branching tends to burn really well. Cyclic compounds, aromatic compounds, these ones here burn better. So these ones here are better used as fuels. And what we can do is we can take what would have been just the straight chain alkanes here. We could run it through those processes. For example, remember we saw on the slides here, I can take a straight chain hexane like that. I can do cyclization. I can end up forming a ring of it. I can end up forming like a 6-carbon ring. Doesn't need to be 6. In the second case here, I can do aromatization. I can actually make it an aromatic. That's why I like the 6 here. And just anything that I do to increase branching, have more rings to the structure. It can even have multiple rings here. Generally ends up as a better fuel. So some more details here you can look through. Here, for example, they're taking our octane as we would imagine. This one here is now isooctane. If you remember, this isooctane was the thing that I graded with octane rating 100. So if I can take the straight chain, it doesn't burn really well, through a process of isomerization. So basically I'm going to form structural isomers. I might still get a mixture. I'm going to slowly isolate the isomers and then slowly purify for the more branched compound that I want. So some other processes there. Although cracking does take a big molecule and ends up making a smaller molecule. As you flip to the backside here, cracking can also be done in reverse. So in this case here, it just shows regular cracking. It's going from a big molecule to a couple small molecules. We just talked about only forming one alkene. You could hypothetically do this in reverse. You could actually get starting with the alkene and the one alkene that I would have formed, and it's almost like an addition reaction. It's almost like in this case here, we have the double bond. That's an electron dense region here. That double bond here might try to grab the hydrogen. I end up forming a radical, and then in that case there, from that radical, that single electron might end up adding to the carbon on the other side. So it's like addition across alkenes, but this time we're actually adding a whole alkane. We're gluing 2 parts together here. So cracking can be done reversibly. It can go in both ways there. We talked about on our slides, unfortunately, coal. So think about that. That's just solid carbon, right? Although it is really high energy density, high specific energy as well, that one there, unless we have a huge, large-scale power plant, I can't actually extract that energy efficiently enough. So what we do is 2 processes. We're going to start off here with the process of coal liquefaction. Basically taking coal, we're going to convert it into liquid fuel. This is what we saw. We took carbon, we reacted with just hydrogen. The n's and the n+1 can be any ratios. This gives us the balancing of the coefficients. And it ends up forming alkane, right? That's our general form for an alkane. And the reason why they specify here n greater than 4, remember, only after butane, let's say I have a C5 and onwards, these ones here are actually liquids under our regular exposure. C1 to C4 are still gases. That wouldn't be coal liquefied. That would be more so coal that's been gasified. There's an example of that one there. It's called the Fischer Trope process. This is also a coal liquefaction. We can produce various alkanes. This time we're going to take that synthesis gas mixture. Again, make sure you know that actually came out of carbon and water reacting. But those guys can also be your precursors. You can burn that directly, or you can somehow combine those together, and they can also form alkanes. Again, I want the n bigger than 4. This one ends up generating water as well. These reactions here, they do ask you fairly commonly, so make sure you know at least a reaction for what does coal liquefaction look like. So let's call that A. Coal gasification, I have it down here, so let's call this B. Similarly, sort of same idea. We're going to take solid carbon coal here, and we're going to put it into the gas state. Gases are a lot easier to extract the energy off of it, and they demonstrate for you what could happen. So I take the solid carbon that I had. That's just a coal. I got to react it with water. This is how one way we can generate synthesis gas. It's not the only way. Again, the synthesis gas can be used directly itself. You can just burn it as a fuel directly, or what you can do is you can take this as a precursor, you can react them away and actually form alkanes with it. So either the synthesis gas makes the alkane, or sometimes even this carbon and water, if you compare reaction 1 and reaction 3, sometimes that directly can also make methane. They're just showing you one example of an alkane. We know that here, this one here is between C1 and C4. That way we can make sure that it's actually a gas, that's why it's been gasified. And in this case, why we like methane, sometimes we call methane here natural gas as well. Methane is the primary component of natural gas. Although burning fuels here generally always release CO2, it tends to be more environmentally clean. So in this case here, just do a little sum up here. Natural gas here is one of the cleanest fossil fuels. It has a very high hydrogen to carbon ratio, so that means it's very saturated. Lots of H's, so if I have CH4, I have 4 H's per any just one carbon. It can flow very naturally. Not only it's a gas, it's fairly small molecule, so it doesn't have really high London forces. It produces very minimal CO, even though the synthesis gas here was used over the course of the reaction. It produces very minimal byproducts that might actually pollute the air. And then definitely note here methane. We know it's CH4. It's the primary component of natural gas here. Because it is a gas, we also need to worry about those impurities and purify them and whatnot. They say experimentally really easy to pull off the nitrogen and sulfur impurities. We saw one example of the impurity as H2S there. And basically it's either you liquefy coal and you use that as fuel for your automobiles, or you gasify it. We use this fuel here for our Bunsen burners, for your propane stoves, barbecues, things like that. We're putting the carbon, we're able to access all the energy from the carbon with a little bit more ease. So I'm going to end off this lesson here just with a show of how do we do this carbon footprint. Again, carbon footprint is just one measure of how much carbon I'm actually putting in to the air. Again, it's worded as equivalent tons of carbon dioxide. So let's just practice here. Let's say during a barbecue, we happen to use 750 grams of propane, C3H8. Let's say we use about that amount every time we do a barbecue, and let's say I do 2 barbecues a week. So maybe it's summertime, maybe everything is nice. In this case here, because I do want to eventually do equivalent tons of carbon dioxide, I do want to write out the equation. Let's start off with propane. We assume complete combustion, so it reacts with O2, forms CO2 and water. We do our balancing here, right? I'm going to be using the enthalpy of combustion. Maybe not even. So let's do a 1 here. We're going to go 3, a 4. I have 10 oxygen, so I'm going to need a 5 there. And basically what I want to know, if I'm asking you, can you calculate the carbon footprint? For doing this, we're going to do a silly example. Let's pretend we did this every week in the year. So in the year we have 52 weeks, so even wintertime, springtime, whatever. Let's pretend we still barbecue twice and we use 750 grams every time. To calculate the carbon footprint, the unit on this side is going to be what is the equivalent tons. Ton is 1,000,000 grams or 1,000 kilograms. What is the equivalent carbon dioxide? And there is this notion here, this is annually produced. Not just for you doing the barbecue once, but doing this barbecue here every single week for 52 weeks. So how we're going to do this here, this just ends up as a stoichiometry problem. We're going to start off, well, I do 2 barbecues a week, and every time I do this barbecue, I end up burning 750 grams of my propane, C3H8. So 750 grams of this guy. What I want to do is I want to form the equivalent upon burning, upon this complete combustion, how much CO2 do I actually generate? This just becomes a nice mole ratio, a nice stoichiometry problem. Well, if I have grams, let's find moles. So I would need the molar mass of propane here. I would go 3 times 12.01, added to the 8.08 for the 8 hydrogens. I get here 44.11 grams for a mole. Now that I have moles, I can do the mole ratio. For every 1 propane that I burn, I get 3 parts carbon dioxide equivalent. In this case here, it really is forming that product there, but that would be what's called an equivalent carbon dioxide. And then I need this in terms of grams, so I would need the molar mass of carbon dioxide. I believe it's 44.01. So 44.01 grams. So that's pretty close now. Most of the units are canceled out. 2 barbecues a week, gram, gram, mole, 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 mole. And now I have grams. And now lastly, I just want to convert to tons. If you're not familiar with that unit here, again, 1 ton is actually 1,000,000 grams, or you can say 1 ton is 1,000 kilograms. So it's like 1,000, right? So far this is just giving me equivalently, if I do this burning here for 1 week, right? For 1 week, I barbecue twice. Every time I use 760. Unfortunately, I still have grams. I'm just going to convert the units. Well, since 1,000,000 grams makes a ton, that unit also cancels out. That's how many equivalent tons of CO2 I'm putting in the atmosphere for 1 week. And lastly, I'm just going to say, well, because it is annual, I'm going to multiply by 52. Let's just punch our way all the way through. Let's find our carbon footprint if we did this. Lots of barbecuing throughout the year. Double check my numbers here. I'm getting my carbon footprint, my equivalent tons of carbon dioxide I'm tossing in. I'm getting 0.233 equivalent tons of carbon dioxide. And that number there is called your carbon footprint. If you look, in this case here, this is just a food analogy. What about your transport? What about burning those fuels? That would add extra equivalent tons of carbon dioxide. If I add up all that per person per year, that's called your carbon footprint. Again, we do want to be more environmentally conscious, so if we can, we want to limit our carbon footprint if we can. Right? So that finishes off us for C2. If you have any questions, just let me know. Thanks, guys.